Welcome to this session of energy conservation and management. Myself, Anirban Sarkar, Assistant Professor in Mechanical Engineering Department of JIS College of Engineering, Kollam. In today's session, we will discuss case studies of different industries, how they implemented different energy conservation methods to achieve the goal of the energy conservation. First case study, that is for a glass manufacturing unit. In this unit, the glass industry as a whole, the glass manufacturing as a whole in our country consumes approximately 300 trillion BTU per year, that is British thermal unit per year, and some sources estimated that as much as 70% of this energy consumption is devoted to glass melting and refining processes in high temperature furnace. Furnace vary widely in the energy required to melt a ton of glass. The theoretical minimum energy for melting glass is only about 2.2 million BTU per ton. However, some furnaces consume as much as 20 million BTU per ton. Furnaces used in large glass melting operation include directly fired, recapitative and regenerative unit of melters, oxy-fuel and mixed fuel furnaces. Regenerators and recapitators are most frequently used system for waste heat recovery in glass industry. Glass melting is a high temperature operations providing several opportunities for recovery of high grade waste heat. Without heat recovery, stack exhaust temperatures typically exceeds 2400 degree Fahrenheit, that is nearly 1315 degree centigrade. Recapitators and regenerators for combustion air preheating are the most common method for waste heat recovery. Regenerative furnaces employ two chambers with checker bricks. These chambers alternately absorbs heat from exhaust gases and transfer heat to the incoming combustion air. The direction of airflow changes approximately every 20 minutes so that one chamber receives heat from the stack exhaust while the other one rejects heat to incoming air. Final exhaust temperature vary between 600 to 1000 degree Fahrenheit, that is 316 to 538 degree centigrade throughout the cycle. So that means by using these checker bricks, the flue gas temperature of 24 degree Fahrenheit is reduced to 600 to 1000 degree Fahrenheit. which is a very good energy absorption by these bricks. In addition to combustion air preheating, methods for waste heat recovery in glass manufacturing include preheating batch and cullet material and using waste heat boilers for electricity generation. However, these systems are most likely to be used in oxy-fuel flame, where combustion air preheat is not used. Oxy-fuel furnaces use oxygen-enriched air or pure oxygen for combustion. This saves fuel by reducing the energy need to heat nitrogen carried in atmospheric air. When furnaces are adapted to oxy-fuel firing, the regenerators are removed, which can lead to higher exhaust temperature around 2660 degree Fahrenheit, that is nearly 1460 degree centigrade. Although the waste heat is at high temperature, the mass of exhaust gases is much lower, leading to lesser waste heat loss as a percentage of fuel input. In second case study, that is in a cement manufacturing unit. So this figure shows that is a cement kiln preheater. The cement industry consumes about 550 trillion BTU per year to produce 110 million tons of cement annually. The major processes steps include mining and quarrying raw materials, that is mainly limestones and chalks, crushing and grinding materials in preparation for the clinker production, and cement milling. Clinker is the solid nodular material existing kilns and used for production of cement. Clinker production in kilns by far the most energy intensive process in the cement industry, responsible for about 90% of delivery energy consumption and 74% of total energy consumption when electricity related losses are included. Rotary cement kiln are long refractory lined steel tubes and lengths varying from 200 to 1000 feet. The fuel most commonly used is coal, though some kilns use natural gas, oil, and various waste fluids. Raw material, that is limestone and other material, enters at the top of the kiln and gradually passes through increasingly hot zones towards the flame at the bottom of the kiln. Rotary kiln can be divided into two main groups: wet process and dry process. In wet kiln, the raw meal has a moisture content of about 30 to 40%, requiring large energy expenditure for evaporating this moisture into water or steam. These kilns are no longer being constructed and compromise only 20% of clinker production capacity. Dry processes kilns use dry powder mill. The kiln typically has a chain section which absorbs heat from the exhaust gases and enhance heat transfer to the mill. Exhaust temperature without heat recovery are about 840 degree Fahrenheit, that is nearly 450 degree centigrade. Opinions for heat recovery from stack exhaust include preheating mill and power generation. Preheating is accompanied through counter current flow of raw material and exhaust gases in cyclones. The most common systems are series 4-stage preheaters, which have exhaust gas leaving approximately 640 degree Fahrenheit, that is 340 degree centigrade. Exhaust gases are in the medium temperature range, where there are still opportunities for waste heat recovery. Additional stages of preheaters can further lower temperature. If 56 stages are used, exhaust temperatures can be reduced to 400 to 570 degree Fahrenheit. That is 200 to 300 degree centigrade. The number of preheat stage is often limited by increasing complexity and structural limitations associated with each additional stage. Exhaust gases can also be used for drying and preheating clean feed into the raw grinding stages. In this plant, in cement manufacturing, cogeneration instead of mill preheating is another option for heat recovery. Currently, 4 plants in USA have cogeneration system generating 486 million kilowatt, that is 1.66 trillion British thermal BTU annually. All these systems use steam cycles for electricity generation. However, alternative cycles, including the organic Rankine cycle and Kalina cycles, are receiving increased attention for their ability to work more efficiently with low to medium temperature exhaust ranges. These can be used for recovering heat from combustion exhaust gases, that is after mill preheater, or from the clinker cooler. While heat recovery from cement kilns is common, about 83 trillion British thermal unit per year of medium temperature waste heat still undercovered from clean off gases in the USA cement industry. These waste heat losses can be reduced through the installation of additional preheating stages or by using cogeneration technology. Another opportunity for increasing clean efficiency is through optimizing waste heat recovery in the clinker cooler. Clinker is discharged red hot from the kiln and transferred to clinker cooler, which performs the dual function of cooling the clinker from downstream transport and processing, as well as recovering heat energy contained in the clinker. The most common clinker cooler design are gate type designs. Recirculating air cools the clinker from about 1800 degree Fahrenheit to 200 degree Fahrenheit. That is 1200 degree centigrade to 100 degree centigrade. These hot air are discharged from cooler is used to heat secondary air in the clean combustion or tertiary air for the pre-calciner. These systems typically recover about 11.3 million British thermal unit per ton of clinker. The recovery efficiency of clinker cooler can be enhanced through reducing excess air volumes, properly control the clinker bed depth, optimizing gate designs, and controlling the air distribution over the gate. These measures can save an additional 0.1 million BTU per ton. Meanwhile, organic Rankine cycle and Kalina cycles are also emerging opportunities for heat recovery from clinker cooler exhaust. In third case study, we have iron and steel manufacturing. The US iron and steel industry consumes approximately 1900 trillion BTU of energy per year, with an average energy intensity of 17.4 million BTU per ton. The industry employs several high temperature furnaces for sinter, coke, iron, and steel production, which accounts for about 58% of industry's energy consumption. While recovery from clean gaseous stream in the industry is common, heavily contaminated exhaust gases from coke ovens, blast furnaces, basic oxygen furnaces, and electric arc furnaces continue to present a challenge for economic waste heat recovery. Heat recovery techniques from these dirty gaseous streams are available, yet implementation has been limited due to high capital investment costs. The investigated waste heat losses in both integrated steel mills and mini mills. In regarded steel mills, which account 54% of raw steel production in 1999, processes analyzed include coke making, blast furnace iron making, and basic oxygen furnace steel making. In the mini mill, exhaust gases from electric arc furnaces were analyzed. Waste heat from these processes total about 79 trillion BTU per year based on a reference temperature of 77 degree Fahrenheit, that is at 25 degree centigrade. Now, this chart shows unrecovered waste heat and work potential from selected process exhaust gases in the iron and steel industry. So in a coke oven, the annual energy consumption is 65.5 trillion BTU, and in that coke oven gas and includes coke oven waste gas. The temperature ranges for coke oven gases in between 1800 degree Fahrenheit and in degree centigrade 980. Coke oven waste gas 392 degree Fahrenheit. Waste heat, that is trillion BTU per year for coke oven gas 15.8 and coke oven waste gas, that is 11.2. Now, with the work potential, if a device has Carnot efficiency of 0.8 in case of recovering coke oven gas, so work potential, that is 12.1 trillion BTU per year. And similarly, for an coke oven waste gas recovery device, it has, if it has Carnot efficiency on an average 0.4, then work potential will be 4.1 trillion BTU per year. For blast furnaces, that is energy consumption annually, that is 642.3 trillion BTU per year. Now, these blast furnaces, that is blast furnace gas, have high temperature as high as, that is 430 degrees centigrade. Now, work potential from this blast furnace gas is, that is 1 trillion BTU per year, considering the Carnot efficiency of the device which recovered the waste heat, that is only 0.19. So much development needs in this sector. And with recovery, another 0.8 trillion BTU per year of work potential energy we can get. And there is no recovery still now, that is the work potential, that is 4.6 trillion BTU per year. Now, for basic oxygen furnace also, there are work potential about 23 BTU per year. For electric arc furnace also, that is with recovery, that is only 0.1 trillion BTU per year, but the no recovery is 4.6 trillion BTU per year. So as a whole total, with recovery and with no recovery, if we all this energy, if we can recover, so total work potential, that is 49.2 trillion BTU per year energy we can save. And total with respect to energy consumption of 828.6 trillion BTU per year. Now, in another case studies which has integrated steel mills. So in integrated steel mills, we have, that is coke oven first of all, and next is a blast furnace and a basic oxygen furnace. So in a coke oven, producing coke, an essential fuel for blast furnace operation, is a key step in iron making process. Coke is produced in coke ovens where coal is heated in a oxygen limited environment. There are two methods for producing coke, that is byproduct process and the non-recovery process. In byproduct process, chemicals byproduct, that is tar, ammonia and light oils in the coke oven gas are recovered, while the remaining coke oven gas is cleaned and recycled within the steel plant. In a non-recovery process, all the coke oven gas is burned in the process. The most common type of process is still the byproduct process, which is the focus of our discussion here. Byproduct coke making process has two sides of sensible heat loss. Number one, that is coke oven gas that is cooled in the gas cleaning process. Number B, waste gas existing the coke oven. The coke making process employs several coke oven chambers separated by heating fuels. Recycled coke oven gas and sometimes other gases such as blast furnace gas are used as a fuel source in the heating fuel and supply heat to the oven chamber where coal pyrolysis takes place. As coal is pyrolyzed in the oven chamber, gas and moisture, which is account 8 to 11% of mass of charged coal, are driven off and exist through the drainage pipe. Typical composition of these coke oven gases are shown in the next table. The coke oven gas has a high heat content ranging from around 500 to 700 BTU per square feet. Therefore, it can be recycled and used as a fuel after undergoing a rigorous cleaning process. So this is the schematic diagram of an coke oven where the cokes are manufactured. The hot coke oven gas, it has raising temperature from 1200 to 1800 degree Fahrenheit, and the waste gas that is at 400 degree Fahrenheit. The temperature of crude coke oven gas at the oven outlet ranges from 1200 degree Fahrenheit to 1800 degree Fahrenheit. At this point, the gas is the source of sensible heat. However, the heat is universally wasted due to the high level of tars and other materials that would build up on heat exchanger surface. Upon leaving on oven, these gases is cooled by ammonia liquid spray followed by primary cooler. Various technologies are then used for removing tars, sulfur compounds, ammonia, and light oils. After cleaning, this coke oven gas is used as a fuel throughout the plant. In this arrangement, only the chemical energy of the COG is recovered when recycled, while the sensible heat is wasted. The total sensible heat lost from COG in the United States is approximately 16 TBtu per year. While facilitating to employ heat recovery from this coke oven gas, a limited level of heat recovery is possible, as demonstrated by the success of this practice in Japan. Facilities in Japan have successfully applied heat recovery through use of low pressure heat transfer media. In general, the minimum allowable temperature of coke oven gas in the heat exchanger at about 840 degree Fahrenheit, that is 450 degrees centigrade. At lower temperature, tar condenses and leads to soot formation on the heat exchanger surface. Cooling to this enables only about 1/3 of sensible heat to be recovered. It is unlikely that integrated steel mills in the US would pursue new technology for heat recovery from crude coke oven gas. Not only will the industry face cost barriers with heat recovery from dirty exhaust steam, but the byproducts of coke making process may become irrelevant in future years. it is the likely that the industry will move away from the byproduct process to the non-recovery process due to environmental consideration. In the non-recovery process, the COG gas will be burned within the process, and a waste heat boiler used to recover the sensible heat of the off gases. Another source of sensible heat loss in the coke oven is the waste gas from the combustion of recycled gases. This recycled gas is used as a fuel in the heating fuel which is adjacent to the oven chamber. Combustion of this coke oven gas generates hot exhaust gas which leave the oven flue and pass through a regenerator to transfer heat to incoming combustion air or fuel. Waste gases leaves the regenerator at temperature average around 200 degrees centigrade. In some cases, mainly outside country, the heat content of the waste gas are further recovered by using a heat pipe. Or preheating coal charge and reducing its moisture content. The temperature of the exhaust gas dropped 60 degrees centigrade only. The waste heat loss from the coke oven waste gas in US is estimated about 11 trillion BTU per year. Now the next part is blast furnace. The major unit of the integrated steel is the blast furnace, which converts iron ore into pig iron. Raw materials are charged from the top, including iron containing material, additives, and coke. While hot air and supplement fuels are injected into the bottom of the furnaces, the burden moves down through the blast furnace and meets a rising current of hot gases. The hot air entering the furnace is provided by several auxiliary hot blast stoves. In the blast stove, fuel such as blast furnace gas and coke oven gas are combined. The heat from the combustion exhaust is transferred to the checker work regenerator. When the regenerator reaches an appropriate temperature, the flow of air is revised and cold air is forced through the regenerator, which transfer heat to the cold air. The heated air is then injected into the furnace. The system operates according to the same principle as a regenerator used for heat recovery. However, in this case, it is not a waste heat recovery device, but rather the mechanism of transferring heat from the stove to the hot blast. Sources of hot gas waste heat in blast furnace includes both the exhaust gas from the hot blast stove and the blast furnace gas leaving the blast furnace. Here, sensible heat loss from the blast furnace gas is estimated about 5 trillion BTU per year. These gas consist of approximately 20 to 28% of carbon monoxide, 1 to 5% hydrogen, and inert compound, as well as dust, sulfur, cyanides compound, and other contaminants. Older blast furnace had higher exhaust temperature around 400 degrees centigrade. New furnaces have been designed for most efficient heat transfer. Consequently, hot gases are in low temperature range. Several power plants recover blast furnace gas for the use as a fuel in the blast furnace, hot mill reheating furnace, coke oven heating, power production, etc. So this blast furnace gas must be cleaned before entering into the other section, which is generally accompanied via wet cleaning, and with the result that sensible heat of gas is lost. An alternative to wet cleaning technology is dry cleaning, in which temperature of the gas entering the TRT can be raised at about 250 degree Fahrenheit, that is 120 degrees Celsius. Dry tap type TRT technology, that is top pressure recovery turbine, is already commercial, however being significantly is the expensive in expensive device. Another opportunity for waste heat recovery is the combustion exhaust gases leaving the hot blast stove. The gases are at temperature of around 250 degrees centigrade. The blast stove exhaust gas is relatively clean and more compatible with the heat recovery device, making heat recovery from blast stove a more common practice. Next is basic oxygen furnace, which is uses oxygen to oxidize impurities in the pig iron such as carbon, silicon, phosphorus, sulfur, and magnesium. Operation is semi-continuous. Hot metal and scraps are charged to the furnace. Oxygen is injected, fluxes are added to control erosion, and then the metal is sampled and tapped. The temperature required to melt the metal is supplied by the exothermic oxidation reaction. Therefore, no external heat source is needed. These off gas from the basic oxygen furnace are at high temperature and account 27 trillion BTU per year of waste heat in US. This gas has high concentration of carbon monoxide and like coke oven gas and blast furnace gas. These gases offer opportunities for recovery of chemical energy and sensible heat. Challenges to waste heat recovery in these gases includes, that is, high capital cost and substantial maintenance problem resulting from hot dirty gases. The most common practice of this flare of blast furnace of gases, however, varies. Commercial method of waste heat recovery are used in Europe and Japan. There are two methods, that is open combustion and suppressed combustion. In open combustion system, air is introduced to the blast furnace gas duct to combust with the CO. The heat generated is recovered by the waste heat recovery boiler. In suppressed combustion method, a skirt is added to the converter mouth to reduce the air filtration. The gas is cleaned, collected, and used as a fuel. It is possible to recover both the gases and the sensible heat via a combined boiler or suppressed combustion gas recovery system. So these are all the case studies of these. Thank you for joining this session.